Alright, so now we're going to look at a special type of bonding existing among metals that account for a lot of the properties of metals and these alloys that we'll mention. But we have metallic bonding, and as you see here in this picture, metal atoms become cations surrounded by a pool of their shared electrons. And this attraction is called a metallic bond. And so essentially, there's as it says here, an electron sea of a metallic crystal. And so because of this, the pool of electrons allows metals to conduct electricity and accounts for its malleability. And these are two of the more important properties of metals, the fact that they do conduct electricity, and we can, mold the metal and by hammering it, and also stretching metals out into wires. And so the ductility of metals. Now here's another one of those awesome visuals showing us some metallic bonds. I know, pretty fancy. We've got the metallic cations and then just this pool, this sea of electrons, and you can see that electrons are moving all around, which again allows for electricity to easily flow through the metal. Now, these metallic bonds in some metals are stronger than others, and this is based mostly on the number of valence electrons that are being shared in that electron sea, that electron cloud. Alkali metals only have one valence electron, so their metallic bonds are relatively weak, and we saw that in the one video that we can actually cut these metals with a knife. They're very soft, and they melt at relatively low temperatures. Sodium, for example, at 97.8 degrees Celsius, which is a lower temperature than the temperature at which water boils. Transition metals like zinc, copper, iron, or tungsten, they have more valence electrons that are shared, so those metals are much harder and melt at a higher temperature. Tungsten, for example, like that meter of tungsten wire in an old school light bulb, doesn't melt until 3,410 degrees Celsius, so much stronger metallic bonds. Now also, we have talked about the fact that metals will form alloys. And again, that's a mixture of two or more metals. And so instead of just having one type of metal, you'll have different types of metal, cations, sharing those valence electrons and creating essentially different metals. Alloy, that's a word you might have heard like with alloy rims on a car. But let's take a look at a couple different alloys. And they're extremely important. We had a whole age in time, a Bronze Age. Bronze is an alloy. But first of all, gold. Gold is actually an alloy. Pure gold is 24 karat. It's very soft and can be easily worn away or dented. Now, really expensive jewelry can be 24 karat, but more often, especially for jewelry that you want to wear on a daily basis, it'll be less than that. 12 karat gold. That's 50% gold and 50% other metals. 18 karat gold, 75% gold, 25% other metals. Usually it's alloyed with silver or nickel, palladium, platinum, sometimes even copper. I'm sure the grill here that we see is pure gold, although it's very soft, and so I would guess not so much pure gold, maybe 12 karat. And that's for our buddy Flava Flav. Yeah, boy. Sorry, I know. Moving on, bronze, like that Bronze Age, bronze is a mixture of copper and tin. And by themselves, those metals are relatively soft, but when mixed together, much stronger, much harder, like the bronze medals at the Olympic game. Brass is made with copper and zinc. And brass is softer than bronze, so it's easier to shape and has a much more appealing color to the eye. It's much shinier, so that's why we have all those musical instruments made of brass. Steel is another alloy. Steel is not just pure iron. Steel usually contains about 0.2 to 3% carbon, and those carbon atoms form bonds with the iron, making it much stronger. Stainless steel doesn't really have any carbon, but can be up to 10% chromium, like stainless steel appliances, lots of stainless steel cookware, etc. If we need steel cables like on a suspension bridge, we need them to be able to stretch and move and sway. So they'll contain some other elements like sulfur or silicon, manganese or phosphorus. And those atoms almost kind of act like little sponges in there to allow the steel to be flexible and move. And then lastly, we have superalloys. And these have been much more important, especially since man has started to take flight and take flight at rapid speeds. As you see there, it's revolutionized the aircraft industry. Rhenium is a very valuable metal that can be added to aluminum and magnesium, and we use those metals in flight a lot because they're light and they are strong. But when we put in some rhenium, it'll keep their strength at very, very high temperatures, like in jet engines here for the Thunderbirds from the Air Force. So that pretty much takes us through the metallic bonding aspect, and thank you very much, and I will be working with you on covalent bonding in the classroom.